Hello again, Armand Pantalone, the Chief Technology Officer at Gigatronics, with another one of our TEmS talks. You heard of TED Talks, well, this is the TEmS talk series. TEmS being our acronym for Threat Emulation System. So today we're just going to show you some simple things on how to build a simple emitter, and then how to build a complex scenario from a whole bunch of emitters. So we'll start with one emitter, and then we'll add a number, and we'll show you how the RF diversity of the system is very helpful. So one of the things we're going to show you real quick is a very simple scenario with just one system under test receiver. It's an airborne platform. It's going to be flying radially into a fixed ground radar site. This ground radar site is actually a sit and spin. It's just a ground-based radar with a circular scan pattern with a directional antenna. So when we execute this simple scenario of just one emitter on a ground platform, a fixed ground platform with an airborne system under test receiver flying directly into it, two things we want to show you. First is the circular rotating scan pattern that we're going to simulate with this emitter, and also how the software handles what are called threshold drops. So it's actually going to be creating pulse descriptor words around the entire 360 degrees of rotation, but because the directional antenna on the emitter is not always pointed enough at the airborne platform flying into it, there's going to be a lot of times when the energy is below a set threshold, and we won't be occupying an available RF channel for a signal that's going to be too low for the system under test receiver to see it. All right, so without further ado, I'm going to execute the scenario, and then I'm going to point to the runtime statistics window. And what you're going to see with this emitter is planned for a 120 degree per second circular scan rate. So what that means is once every 3 seconds, its directional antenna will be sweeping through the system under test receiver. Okay, so when we execute this scenario, the airborne platform will start its run inbound to the fixed ground platform, doing a circular scan at a 3 second sweep rate. So if you point your attention to the runtime stats window, what you'll see is it'll only generate RF once every 3 seconds, as a 120 degree per second sweep rate actually sweeps its directional antenna through the system under test receiver. So if you stay there for a moment, I'll show you what's really going on behind the scenes. It's generating the pulse descriptor words as if it were going to illuminate other systems under test in the scenario, but because there's only one system under test receiver directly inbound, he actually only generates RF once every 3 seconds as he sweeps through, even though he's generating all the pulse descriptor words as if they were used for the whole 360 degree scan. We're going to execute the scenario again, and this time what we're going to show you is this particular emitter is designed to put out 10.15 gigahertz, and what you'll see on the spectrum analyzer display is that once every 3 seconds you'll see a peak as the sit and spin emitter actually rotates its antenna pattern through the system under test receiver. And as the airborne platform gets even closer to the system under test receiver, the amplitude should increase to the max as he flies over. Right about now. And it should come down as he flies past him. The system under test receiver has an omnidirectional radar warning receiver antenna, which is why he still sees energy as he flies past and through them. Earlier we showed you the circular scan ground site on J19, bear site. For those of you with either less time to spend looking at these videos or a shorter attention span, we're resisting the urge of incrementally adding one emitter to this scenario every single time we take a video. So what we did was we jumped right to the point where we added 4 separate emitters into the scenario. They're all ground-based assets with our system under test airborne platform. It's going to fly right through the engagement zone. So for all these emitters, we take our cut sheets. It gives us some of the waveform characteristics and the frequencies at which they operate at. These 4 emitters here are a CW guy at just above 10 gigahertz. We've got another J21. This guy here is just about 16 gigahertz, just above and below. This other guy, H08, this guy has greater frequency diversity. He's got a number of channels just above 5 gigahertz, a number right about 6.5 gigahertz, and then a couple other frequencies just above and below 8 gigahertz. The last one has a number of different modes, all of which are about 6.5 gigahertz. So when we execute this scenario for the 4 platforms and the 4 emitters tied to those platforms with a system under test receiver, you're going to look at the runtime stats and you're going to see the 4 emitters here and all the RF that they're creating. And without further ado, I'll start the scenario off and running. And then I'll switch over to the spectrum analyzer. So this is our live spectrum analyzer of all of the signals being put out cabled into in a lab environment into the system under test receiver. So I'm going to go to max hold. And we're going to let that build up for a few moments. You can see in real time on the runtime statistics, all the emitters in the scenario. Again, remember that number 2 is a sit and spin circular scan antenna. So he only is actually putting out RF into the system under test receiver once every 3 seconds because he's sweeping at 120 degree per second rate. Okay, we've let our scenario run for a little while. Our system under test receiver is now exiting the engagement zone. And if we go to the spectrum analyzer display on max hold, we should see peaks at all of our emitters. And if you remember, we had our sit and spin at 10.15 gigahertz. We had our 16 gigahertz emitter over here. We had a number here between 6 and 8 gigahertz, and then the guy at about 5, just above 5.1 gigahertz. Okay, so this time when we take a quick snip, we'll let you see. We're going to focus on just the H08 bare site, which is the ground platform where the airborne platform is flying radially into. And he has 2 frequencies that he's operating at, just above 5.1 gigahertz. And we'll show you what those 2 look like zoomed in on just that one emitter. So we're off and running. And we'll go to our spectrum analyzer. And we're going to go to max hold. You should see a peak at 5103 and 5150 megahertz. There's 5150 poking up, and there's 5103 in the center, and that other guy on the right is from one of the other emitters in the scenario. And if we were to change the span slightly, you see a little bit better of the pulse, the sin X over S pulsed characteristics of these emitters in the scenario. Based on its pulse width and PRI, you get the perfect sync function. So one more thing I want to show you before we break is to show you the pulse characteristics. We've seen it in the frequency domain on the normal spectrum analyzer display. We're going to put it in zero span mode and show you some of the pulse width and PRI characteristics of H08, the guy that we're flying radially into. So as we've seen, this is our airborne platform flying into our H08 emitter, and we're going to start up in the frequency domain on the normal spectrum analyzer display, and then we're going to switch over to the zero span mode and show it to you in the time domain. So here's both the spectral display and also the time display. The top display, time display, is on zero span mode. So it's triggered on amplitude, and you can see the pulses in the pulse group with both their pulse repetition interval, and we're going to try to zoom in and show you the pulse width, okay? Okay, so now we're going to focus on the top display, which is zero span time mode, and we're just going to progressively step down until you can see the pulse width of the signal. That's all you get. So 1 millisecond time, 5 divisions, 500 microsecond pulse PRI. One of the 2 PRIs. The second one is just slightly bigger. Thanks for joining in today. Maybe in another future installment of TEmS Talks, we'll show you how to build up one of these emitters with its frequency, time characteristics, pulse width, PRI, and if you want to put any modulation onto it too, we'll explain that in another future TEmS Talks. Thanks for joining us today.